Thermodynamic processes. In a thermodynamic process, an ideal gas changes from an initial to a final state following a path through a series of intermediate states. This may be represented on a PV diagram as a curve. At each point in the process, the gas is in a state specified by the coordinates P and V. Over this process, the change in the internal energy of the gas is given by the first law of thermodynamics as delta U equals Q minus W by, where Q is the heat added to the gas and W by is the work done by the gas. The infinitesimal form is du equals dq minus dw by. Recall that for a step in the process, P dV is the infinitesimal work done by the gas due to volume change dV, and that the work done by the gas during a process is W by is equal to the integral of P dV between Vi and Vf. Hence the work done is the area under the PV curve on a PV diagram. This is positive for expansion and negative for compression. A process can follow many paths, but there are some special processes that are especially useful, which are characterized by one variable held constant during the process. First, an isochoric process has constant volume. Its curve on a PV diagram is a vertical line and is called an isochore. Since the volume does not change, the gas does no work. The area under a vertical line is 0, and dV equals 0 at each step. Hence W by equals 0, and by the first law, delta U equals Q for the process, and du equals dq at each step. Now the heat added at constant volume is Q equals NCV delta T, which is the heat added in an isochoric process. Consequently, delta U equals NCV delta T, as we have seen previously. Second, an isobaric process has constant pressure. Its curve on a PV diagram is a horizontal line and is called an isobar. The work done in an isobaric process is especially easy to calculate. It is simply the area of the rectangle under the line. The integral is W by equals the integral of P dV from Vi to Vf, and that's equal to P times the integral of dV between Vi and Vf. Since P is a constant, it can be taken out of the integral sign, and the integral of dV is V, so the result is P times Vf minus Vi, and that is the area of the rectangle. Recall that the area is negative for a compression from larger Vi to smaller Vf. Since P equals constant, the heat added is related to the molar heat capacity at constant pressure, and we may combine this with the first law so that Q equals delta U plus W equals NCP delta T, and dQ equals du plus dW, which is equal to du plus PdV, which is equal to NCP dt. Third, an isothermal process has constant temperature. Its curve on a PV diagram is a hyperbola and is called an isotherm. To find the work done, we integrate W equals integral of P dV from Vi to Vf. From the ideal gas law, PV equals nRT, and we get P equals nRT divided by V. Substitute this for P in the integral, so we have the integral from Vi to Vf of nRT divided by V dV. N, R, and T are all constants, so they are moved outside the integral sign, and the integral becomes nRT times the integral from Vi to Vf of dV divided by V. This integral is log V, natural log ln, log base E. So it's equal to nRT log V evaluated between Vi and Vf, which is equal to nRT times log Vf minus log Vi. By a law of logs, log of Vf over Vi is equal to log Vf minus log Vi, so we can write the final result as the work done by the gas is equal to nRT times log of Vf divided by Vi. Now U depends on T, so delta U equals 0, so the first law gives delta U equals Q minus W by, and Q equals W by. In the fourth process, called an adiabatic process, it is not one of the variables that remains constant, but it is the heat added, Q, that is zero. The curve on a PV diagram for an adiabatic process is called an adiabat. In an adiabatic process, no heat is added to the gas, there is no heat exchange between the gas and its surroundings, and at each step dq equals zero. The first law gives delta U equals minus W by for the process, and du equals minus W by equals minus PdV for each step. Calculations for an adiabatic process are somewhat more complicated than the previous processes and will be studied later. Finally, a cyclic process is any process that starts and ends at the same state or point on the PV diagram, so its initial and final points, its endpoints, are the same point. This process is a closed loop on the PV diagram and is called a cycle. Since the initial and final states are the same, the change in internal energy is zero, since delta U equals UF minus UI, which is zero, and by the first law, delta U equals Q minus W by, so Q equals W by. Around a cycle, there are two opposite directions, clockwise and anti-clockwise, for which the signs of the work done are opposite. A cycle may be split into two processes between the minimum and maximum volumes, one an expansion and the other a compression. If the direction is clockwise, then the work done by the gas in the expansion is larger than the magnitude of that done on the gas in the compression, so the net work done by the gas and the net heat added to the gas are positive. Note that the net work is the positive area enclosed by the cycle on a PV diagram. In a clockwise cycle, net positive heat is added to the gas, which converts all this heat into net positive work, since the change in U is zero. This is the physics basis of a heat engine, which is a device that converts heat into work. If the direction is anti-clockwise, then the magnitude of the work done on the gas in the compression is larger than the work done by the gas in the expansion, so the net work done by the gas and the net heat added to the gas are negative. The net work is minus the area enclosed by the cycle, so net positive work is done on the gas, and an equal amount of net positive heat is rejected from the gas. This is the physics basis of a refrigerator, or a fridge, which is a device that uses work to extract heat.